In the last video, we looked at what it meant for a function to be uniformly continuous, and it seems like it might be a little bit difficult to determine whether or not a function is uniformly continuous. So we might ask ourselves, is there another way or a better way or a different way to decide if it's uniformly continuous? And the answer to that would be yes, right? So if f is a continuous function on a compact set D, so if it's continuous on a compact set, then it is actually uniformly continuous. Right? So if you can go through and argue that the function is continuous, and you can argue that the domain is compact, so the domain is closed and bounded, then you can say, well, we satisfy both of those things, so it has to be uniformly continuous. The next theorem that we have is if we happen to have uniform continuity, if f is uniformly continuous on the domain, suppose that x sub n is a Cauchy sequence in that domain, then the function evaluated at the terms in that Cauchy sequence is also a Cauchy sequence, right? So we have to have f is uniformly continuous on D. Next, let's take a look at something called the extension of a function. So we say that a function f tilde that has a domain E and codomain of real numbers, that this is an extension of a function with domain D if that domain D is a subset of the domain E and f of x is equal to f tilde of x for every value in that subset in that domain D. Right? So really the idea is if we have this function f that's defined on some domain and we extend it, we decide we want to throw some extra things into this domain and define the function for a few extra values. That's like what the extension is. So why do we think about this, or how might this be helpful? Turns out that a function here, f on with a domain that's the open interval from a to b, this function is uniformly continuous on that open interval from a to b if and only if it can be extended to a function f tilde that is continuous on the closed interval a to b. Right? So if we can get continuity on that closed interval, then we have uniform continuity on the open interval. All right, so let's look at a couple quick examples to close out this section. So is f of x equals x squared uniformly continuous on the open interval from -10 to 10? Right. And so f tilde of x equals x squared on the closed interval from -10 to 10. We might make the observation that this is continuous. Right? That's a continuous function on that closed interval. So if it's continuous on that closed interval, then f of x equals x squared is uniformly continuous on the open interval from -10 to 10. Now some of you might have a couple questions and say, I watched the last video and didn't we say that f of x equals x squared is not uniformly continuous? And I would say, yes, we said that it was not uniformly continuous on all reals, but if we make the restriction for that domain, if we restrict that domain to be the open interval from -10 to 10, then we do actually get the uniform continuity. A second example that we have here is if f of x is 1 over x, is this thing uniformly continuous on the open interval from 0 to 1? Right, so is this uniformly continuous on 0 to 1? Right, so can we extend f of x to f tilde of x that is continuous on the closed interval from 0 to 1. Right? That would be an equivalent question, and the answer is nope. We cannot do that. Because we cannot do that, then this function cannot possibly be uniformly continuous on this interval from 0 to 1. All right, thanks guys. We'll talk to you guys next time.